Okay, let us talk a little bit about error magnification in the problems of solution of system of linear equations. So, first of all, as you understand, so if we just write standard system of linear equations in this form, right? So matrix A multiplied on the column vector X equals to P. So let us suppose that using some of the methods, you were able to find some XA, which is approximate solution. How would you control whether this, I mean, what is the quality of this approximate solution? So as you probably remember from the previous, from the root finding algorithms, right? So the forward error there, it was like magnitude X minus X approximate. And we were solving problem like that, right? And essentially we used f of xa as a backward error. Right? So, and then if you remember, so what we were doing, we were considering the ratio of the forward error and relative forward error. So error magnification factor. It was the following: X minus XA magnitude divided by magnitude of X. And here was okay, I just write it like that, relative backward error. Okay, so then now we have different situation, right? So we have, first of all, for example, if we consider exact solution X, right? And subtract our approximate solution, we will get a column vector, right? So this is why we would need to introduce so-called norm of a vector. So if you remember linear algebra well, so we introduce it in the following way. So we can introduce different norms. So for example, we can do it like that. So-called infinity norm. So L infinity norm. So which is nothing else but maximum over all indices of X I minus a x approximate I. So, for example, for the column vector 1, 4, 5, 7, what will be L infinity or just infinity norm? Could you tell me?
Seven?
Yes, just 7. How it will change if I will consider vector like that? Or will it change at all?
Will it not change since you're taking the absolute value?
Exactly, because we are taking, so once again, L infinity norm of x is the maximum over all entries of the vector x of that, right? So this is L infinity norm. Now, so we introduced the way of computing the number, right, out of the vector. So essentially, really there is a theory of norms. So there are some requirements on norms. So the way how you can create a correspondence between a vector and just some real number. So there is a theory about it. So, but I will just let you know that in numerical analysis, there are two. Mostly people use the following two norms. So L infinity norm, which is this, and this, which is called L2 norm, which is essentially, nothing else but the Euclidean length of the vector. So it's essentially sum over all indices just like that. So for example, for our vector, this vector x, L2 norm will be square root of 1 plus 16 plus, could you tell me what will be the next term?
Um, 25.
Right, 25, and then
94, no, 49.
49, right. So this is equal to, let us group this, which will give us 50, right? And so this will give us 50, and this will give us 41, right? Right? So it's square root of 91, which is approximately equals to 9.54. Okay, so you see, numbers can be different, right? So what you need to do? You need to use the same norm when you trying to compute your error magnification factor. So okay, I will also can tell you that nth norm or ln norm, so it's essentially sum I xi to the power n 1 over n. And this is, you can see where this L infinity norm comes from. So if you have different by value entries in your vector, right? So when your n goes to infinity, when it grows, right? So what happens that contribution to this sum from your largest entry in the vector become the major one, right? So as a result, you can just say that this is approximately the maximum over all entries to the power n, right? So, and then when you compute 1 over n power, so you essentially getting nothing else but this expression, right? So as you can see, just the limiting case. So, but as I said, so please take math 464, which is applied matrix theory. Where we study different norms and in the right way prove some theorems about them, and just will prove why the formula which I will discuss right now is essentially, so we will prove that this formula really works. Okay, so we introduced L infinity norm, and now essentially, as you understand the problem of computing the forward error in such a case, is that we don't know exact solution usually, right? Okay, so now let us have a look at the system of linear equation, the original one. So AX equals to B. So how can I write it? I can write it in the following form, or equals to 0, right? So it doesn't matter how you do this. So in your book, they prefer to introduce residual vector. So essentially, this vector describes how your approximate, if you consider your approximate solution like that, right? So it describes how much you haven't satisfied, to what degree you haven't satisfied the original system of linear equations, right? Okay, now, so the norm of the residual vector, for example, L infinity norm, or I can write it as B minus XA. So this is my backward error, right? So as you can see, essentially, if you will consider, for example, this representation of my linear equation, right? So you can see that this is very much like backward error, which we used for root finding algorithms, right? Okay. Now, obviously, when you're solving your system of linear equations, essentially the only way to control the quality of solution is almost only, not exactly the only one, but almost. So it's to use this residue or residual vector. Essentially, this gives you the idea how far from this ideal satisfaction of the system of linear equations you are. So obviously, if you found the exact solution, you will get a zero vector, and the norm of the zero vector will be zero, right? Okay. So I can introduce relative backward error in the following way. It's the norm of the residue divided by the norm of the right-hand side of my system of linear equations. And relative forward error will be difference of approximate solution and the real solution to the infinity norm of the exact solution. And as a result, I can introduce the same error magnification factor which will be relative forward error divided by relative backward error. So essentially, what it tells us, as we discussed, so we can control only these, right? Because we don't know the exact solution, right, of the system of linear equations. So this factor essentially allows us to estimate what will be the relative forward error if you know relative backward error, right? I will show you how to compute this in just a few minutes, but first let us do an example. Okay, so let us consider the following. The following system. So essentially, if I will draw x1, x2, if I will draw two lines, so this is the line, right, and this is the line. So if I will draw them, so they will look approximately like that. So the point of intersection here, as we will show it pretty soon, it will be 1, 1. So is the solution, right? So why? Because what is system of linear equation? We need to satisfy this condition, right? Which gives us one line. And we need to satisfy this equation as well, which gives us a little bit different line. But these lines are very close to each other. Essentially, okay, let me write the system. So what I need to do, I need to multiply this by just when I perform Gaussian elimination and subtract, right? And I will get the following. From here, obviously, I can just rewrite this in the following way. So this is row echelon form, so I can write it like that. So from here, it follows that x2 is equal to 1. And if I substitute it here, I'm getting that x1 is equal to 1 as well. So this is my exact solution, right? Okay, wonderful. Now, let us estimate, let us compute the backward error for the following approximate solution. So the backward error will be okay, so I will just perform on all the computations, and I can tell you that it's minus 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So pretty small entries in the vector, right? So pay attention that, for example, if I consider the forward error, so it will be pretty large. So my x is 1, 1, right? So from here, so this will be 2 minus 2, 0, 0, 0, 1. So it's, so for example, if I will consider L infinity norm of b minus axa, could you tell me what it will be equal to? Just the largest magnitude of all the entries. What is the largest magnitude in this case?
Point 0, 0, 0.
Just this, right? Okay, here. What it is equal to, the L infinity norm.
Negative 2, 0, 0, 0, 1.
No. the norm is always positive, right?
I forgot it's 2.0001.
Exactly. Just remember. So it's maximum magnitude. Okay. So 2 point. Thank you very much. So now let me compute also just for convenience. So okay, B in this case is this, right? Right. So what is L infinity norm of B? Could you tell me what is the L infinity norm of B? I mean, it's not that hard, right? Just find the
2.001.
Right. Thank you. And what is L infinity norm of X? Which is this?
1.
Just 1, right? Okay. So now I can compute error magnification factor, right? Which will be nothing else but relative forward error divided by relative backward error, right? So this will be 2.0001 divided by 1 divided by here is 0.0001 divided by 2.0001. So approximately this will be okay. Now so what it tells us? It tells us that if we are solving this system of linear equations, I mean this system of linear equations using some approximate method, right, of solution. So then how we can solve it? So we will be controlling some norm of this expression, right? So because we don't know exact solution, right? So in general, usually. So in this particular case, we were able to compute it, but usually we don't have it. So, and as you can see, so we have pretty small vector, residue vector, right? So this is nothing else but the residue vector, right? So it's pretty small, but because error magnification factor is huge, so what we are getting that in reality, this it's approximately somewhere. So it's -1 somewhere here. So this is our approximate solution. So we are getting completely different points, right? So just compare exact solution and this is our approximate solution. What is the reason? The reason is that these two lines, they are almost parallel. So as a result, essentially what we are measuring when we are measuring the backward error or residue, we are measuring essentially the distance between these two lines. And because they are almost parallel, so the distance or residue is pretty small, although you are pretty far from your exact solution. So this error magnification factor just tells you that you are pretty far from, even if you even if your backward error which you're controlling is pretty small. So I will look, it's 10 to the minus 4 approximately, right? So, but the thing is that error magnification factor is of the order of 10 to the power 4, right? So you're getting huge error of the order of a relative. So you can estimate your error and I mean the relative forward error, and you're getting that relative forward error is 200% approximately, right? Because it's 2, right? 2, it's, if you express it in percents, it's 200%. So it's huge. So your solution, your approximate solution has no sense essentially. But the thing is that the system is said to be so bad conditioned, so because error magnification factor is huge, so that essentially you cannot use the relative backward error as any reasonable measure which allows you to estimate your forward error, just like that. So now let me introduce, first of all, let me introduce the norm L infinity norm of a matrix. And this L infinity norm of a matrix, it's essentially the matrix A, maximum absolute row sum. Okay. So, for example, this is the matrix which we considered 1, 1, 1. So, could you tell me what will be the L infinity norm of this matrix?
Uh, 1.001.
No, so have a look. You're almost right. So maximum absolute row sum. So you need to take all entries in the row, right, and compute the sum of their absolute values. So here it will give us 2, right, and here it will give us 2 these, right? So the result, the L infinity norm is this. Okay, so I will just declare it so you can find it using MATLAB or whatever, or by hands, so that this will be the inverse matrix. And correspondingly, L infinity norm of A inverse will be, here is a small error, just like that. So could you tell me what is the L infinity norm of inverse matrix in this case? So once again, you need once again, you need to compute sum of absolute values for all rows and take the maximum sum. So in this case, here, sum of absolute values of entries of all of the first row, what it will give you?
20,000?
Hmm?
20,000?
Yes, just this. And here, what will be the sum of absolute values?
20,000.
Right. So as a result, what will be the L infinity norm of A inverse?
20,001.
Right. So the result, so this is what we got, right? And now let me introduce a definition. The condition number of a square matrix A, which is denoted as condition of A, is the maximum possible error magnification factor for solving AX equals to B over all right-hand sides B. Okay, now I will just give you the formula. Condition number of a matrix A can be given as norm of A multiplied by norm of A inverse. So really, you can compute this condition number over different norms, but usually you need to use the same norm. So you can introduce also different norms for for the matrices. So we just introduced only infinity norm, L infinity norm for the matrix, but you can introduce L2 norm or Ln norm for the matrix. So essentially, you just need to use the same norm for the matrix as you use for evaluation of your norms of your vectors. For example, here I use L infinity norm, but I could use L2 norm. So you just need to use the same norm. So essentially, because we are using L infinity norm, so then I can prove the following fact, that so error magnification factor using infinity norms, so can be written as condition number of A, so which will be infinity. So here the same norm is used for errors. Here you see I use the same L infinity norm everywhere. And if you, so we computed this 2, 0, 0, 1. So we computed these infinity norms, and this is multiplied, and so which gives us exactly the value for the error magnification factor which we obtained before for some given approximate solution, right? So you see, really, just looking at the coefficients matrix of the system and computing this condition number, you can get the error magnification factor. So in your book, there is a proof of this statement that this will be error magnification factor. So, but I will omit this proof. So if you like, you can read it. It's relatively simple. So, but I prefer to omit it. Okay. So essentially, idea is the following. If you will have a look at your matrix, so this matrix has very close rows, right? So it means that coefficients will give you almost parallel lines, like here. And then, because normally what you can control is only the backward error for the system of linear equations, so which is essentially distance between the lines, right? So in the point in the point of approximate solution. So then what you will get that this is not a very good way of controlling the forward error, because the magnification factor is huge. So in your in MATLAB, you can use just the function cont A. It will give you condition number in infinity norm. So also you can make your MATLAB to compute condition number with respect to practically all other norms as well. So just read the help for cont operation. So once again, this is extremely important way. I mean, extremely important topic. So essentially, your matrix, the coefficients matrix, controls the error magnification factor. So have a look. The definition of the condition number is the maximum possible error magnification factor for solving AX equals to B. So essentially, just computing the condition number of a matrix, you can figure out whether the, for example, relative backward error is a good way to control the error of your approximate solution, the forward error of your approximate solution. And usually, in most of the cases, you have nothing else but the backward error. So it means that solution of the problems with large condition number so is not that that easy. You have to be a little bit more cautious. So essentially, if you will have a look at this condition number, so it's of the order of 10 to the fourth, right? So if you will try to solve this system of linear equations, which we had, so with one of the methods which we shall study a little later, so these iterative methods. So what you will get? You will get, if you will be using double precision, for example, if you will be using double precision, so you will lose approximately, so this is of the order of 10 to the fourth, right? So in double precision gives you 16 digits, right, approximately. So, okay, not like that, but just 16 digits. So as a result, you can guarantee approximately this, so which is equal to 12 digits of solution. So from the first point of view, it's enough for any engineering application, right? The only problem is that not always you have a possibility to use double precision. So as I told you already, so the standard for microcontrollers which are used in embedded applications, for example, so to give you, for example, in GPS devices, in car computers, multimedia centers, and so on, there mostly people use relatively simple processors, and in many cases they have only single precision. But for single precision, you have approximately 6 digits in single precision. So the result you can get only 2 digits of solution. If this condition number is so large. So this gives you the possibility to get in trouble, right? So essentially, and this is the problem. So you have to understand that although the maximum, the only thing, essentially, almost only thing which you can control is relative backward error. So, but you can compute the condition number, and it will give you the worst case scenario for your relative forward error, which usually is of interest, right? Because you need to know how your approximate solution differs from the exact solution. So this condition number is a possibility to figure out how to, using just the relative backward error, to get the worst case approximation for the relative forward error. Why worst case? Because have a look. in the definition of the condition number, it says that this is the maximum possible error magnification factor. So really, of course, you can get, in some cases, you can get it a little bit less. So, but this gives you essentially more or less how many digits you can get in your solution. Okay, now there is also another problem when you're doing computations, another source of error. So here you can see that the source of error is just the fact that this source of error comes from the fact that our system describes equations which are pretty close to each other, right? So here you can say that this is 1 and 2 here in the right hand side. So, and this equation is almost the same, right? So as a result, what you're getting, two close equations which correspond to two almost parallel lines, and you're getting huge error amplification. So, but pay attention that here you cannot get rid of this problem practically in any, I mean, you can, there are ways to improve this but situation, but not, you cannot improve it too much. So it's just the problem itself which is ill-conditioned. You remember, ill-conditioned means that small errors in the data, in the initial data, are magnified to the large errors in the solution, right? So here, the problem itself is ill-conditioned. So now there is also another thing. So another source of errors, which is coming just from, not from the problem, but it can come from the way how we store numbers, floating point numbers. So, for example, let us consider the following system of linear equations. Just this. So why I took this 10 to the minus 20? Because from the point of view of the IEEE 754 standard, this is almost, I mean, not that far from zero, right? Because, I mean, if we compare this and that, and if we take, for example, x1 equal to 1 and x2 equal to 1, right? So really, we will get, so 10 to the minus 20 by 1 plus 1. In the double precision, this will be nothing else but 1, right? Because remember, so how many digits for double precision you keep? Just 16 digits, right? So the difference of this sum will be in 20th digit, right? So from 1. So as a result, double precision will not feel this difference, right? So as a result, this, for example, x equal to 1 and x1 equal to 1 and x2 equal to 1, right? Although analytically we know that this is not right, right? So, but our computer will not be able to distinguish these two numbers. So 1 plus 10 to the minus 20 and just 1. Okay, so this is this is just a simulation of the problem in which we can get if we are solving. So, for example, our matrix of coefficients can be result of some previous computations, right? And instead of exact 0 here, we can get some really small number. Okay, now if we're just following just standard Gauss approach, so what we need to do, we need, if we are not doing anything special, so we just multiply this by 10 to the 20 and subtract, right? So we will get 10 to the minus 20, 1. Here is 0. Here is 2 minus 10 to the 20th. 1. 4 minus 10 to the 20th. Something like that. So from here, from the bottom equation from here, we can get that x2 is nothing else but 4 minus 10 to the 20th divided by 2 minus 10 to the 20th. So, okay. So, exact solution. So, here, if you will have a look, right? So you can just substitute this into the equation for x1, and you will get something like that: 10 to the minus 20 x1 plus 4 minus 10 to the 20th divided by 2 minus 10 to the 20th. So this is this equation, right? So from here, I can get that x1 equals to 10 to the 20, 1 minus 4 minus 20 divided by 2 minus 10. Okay, so if you will bring it to the common denominator, you will get the following. It will be minus 2 multiplied by 10 to the 20 divided by 2 minus 10 to the 20. Okay, so it means that exact solution is approximately 2, 1. Why? Because have a look. This is large number, right? And this is large number. So with respect to these numbers, these are not that important. And as a result, this will give me approximately 10 to the negative 10 to the 20 divided by negative 10 to the 20, right? So it will give me approximately 1. Here, I can essentially get rid of this part because it's small with respect to this negative 10 to the 20. And then if I divide, I will get approximately 2, right? Is it clear or not how I do this?
Yes.
Okay. Now, in double precision. So what happens? Essentially, when we perform, after we perform this, so what we are getting is equation for x2, for example. So you're getting have a look. You're getting this multiplied on that, right? I mean, this multiplied on x2. So 2 minus 10 to the 20 multiplied on x2 equals to 4 minus 10 to the 20. But the thing is that this and that will not be kept in double precision, because have a look. So the difference between, the difference between negative 10 to the 20 and 2 minus 10 to the 20 is beyond the double precision accuracy. So there, double precision, as you remember, keeps approximately 16 digits after decimal point, right? So as a result, this is what you will get in double precision. So x2 is equal to 1. And the top equation, the equation for x1 becomes so as a result, this and this cancels, and you're getting that x1 is approximately 0. So in double precision arithmetics, you are getting 0, 1. So if you will compute the error, right? So it will be, pay attention, 2, 1 minus 0, 1, L infinity norm divided by L infinity norm. Okay, what will be the L infinity norm of this forward error?
2.
2.
Right, 2. And what will be L infinity norm of the exact solution?
2.
2. So we got that relative error is 1, which is 100%, which is huge. So essentially, it means that you don't have the solution. So if you have 100% error, so you cannot believe in any digit of your error of your solution, right? So none of the digits can be guaranteed. So essentially, so if you have 10% relative error, so it means that you can believe at least in one digit of your solution approximately. But if you have 100% error, so it means that you lost all the accuracy of the solution. So now, so but this problem can be easily amended. Essentially, why we got all these troubles? Because in order to perform Gaussian elimination, we had to multiply by the huge number, right? The first row by the huge number. So if we first exchange rows, so then we will get 1, 2, 4, 10 to the minus 20, 1, 1. So I told you that if you exchange rows, so nothing changes, right? So essentially, so the system will be equivalent, which means that the system will have the same set of solutions. So now we need to multiply by 10 to the minus 20 and subtract, and we will get 1, 2, 4, and here is 0. Here is 1 minus 2, 10 to the minus 20, and here is 1 minus 4, 10 to the minus 20. So in double precision, this is 1. And this is essentially also 1 in double precision. Why? Because we need to subtract from 1 4 to the minus 20, and we know that the difference will be in 20th or 19th digit of the decimal point, but double precision keeps only 16 digits, right? So as a result, we are getting x1 plus 2x2 equals to 4, and x2 equals to 1. So if we substitute it here, so we will get that x1, x2 equals to 2, 1, which is our approximate exact solution, right? So difference, there is a difference, but it's negligible. It's negligible in the double precision. So double precision cannot fill this difference. But this is not exact answer, but error here is very small. So essentially, idea is the following: when you perform Gaussian elimination, exchange your rows first in such a way that in the top left you have the largest entry in the first column, and then perform the Gaussian elimination, and just continue doing this, so to avoid this amplification of errors like we had here. So this problem is relatively easily amended, so we can solve it relatively easily. So okay, so we consider two sources of error today. One is the condition, the error amplification factor, which comes from condition number, right? And another comes from just it's so-called swamping. So which comes just, we need to, from the fact that we need to avoid adding and subtracting very close numbers, right? So, and we would like to avoid multiplication on huge numbers like we had here. So that's it. So, but this problem is I mean, you can get rid of it relatively easy. But the problem with the condition number, unfortunately, it comes from the formulation, from the original formulation, and there essentially there are just a few. I mean, practically nothing you can do there, almost nothing, not exactly, but almost nothing. So okay, is it clear or not? So what I discussed today. Any questions? Okay, so now let me consider an example of application of systems of linear equations to some real problems. So for example, like that. We consider 2-point boundary value problem. So which means that we consider, so this is second derivative. So we consider this differential equation, and we have on the x belong to the interval from a to b, and we know values of our function which we are trying to find, and at the ends of the interval. So we are trying to solve it. So okay. So as you did already. Okay. So in your I believe homework 1, so you had approximation of the derivative over the homogeneous grid, right? So let us do the following. Let us consider endpoints, homogeneous grid. Okay, if we have endpoints, so this is A, this is B, and we just split into homogeneous grid, which means that delta x here equals to delta x here, and so on. So how many, if we have n points, how many intervals we have? So how many intervals like that we have? If we have n points.
P minus A over N.
So altogether n minus 1 intervals, right? Because pay attention that one of the points will be used for the boundary, right? So because, for example, this is 1, 2, 3, 4, and so on. And here is n minus 1, because we start from 0, right? From here. So, okay, essentially delta x will be b minus a divided by n minus 1, right? Then what I can do, I can say that if we start, okay, so the only thing is, let me count it differently. Like that. 1, 2, 3, 4, and so on, till the so b is nth point. Then I can write that xk equals to a plus k minus 1 multiplied on b minus a divided by n minus 1. So this is nothing else but delta x, right? So then if we substitute here, for example, k equal, so x naught, so k equal to x1, sorry, x1, so k equal to 1. So we are getting that this is nothing else but a. And if we substitute here k equal to n, we are getting that this is nothing else but b, right? So k goes from 1, 2, and so on till n. Okay, so I introduced the grid, and on the next lecture we will consider so-called finite difference approximations of the derivatives, and which you had before, so in your first homework. So, and then we will see that really solution of this differential equation become equivalent to solution of some system of linear equations with specific metrics. Okay, thank you. I will stop here.